Hello, my name is Marcello Garbo, a master's student at San Francisco State University working in the lab of Dr. Michael Enright. And I'm excited to present to you my work on From Atomic Design to Infrared Light, Sustainable Synthesis of Indium Arsenide Quantum Dots. So, what motivated me to get into this work? In the status quo, taking a medical image through something like an MRI costs patients thousands of dollars, use heavy metal contrast agents, have limited use with metal implants, and cost millions of dollars to install, with hundreds of thousands of dollars in annual operating costs. And scientists are always looking for ways to see what's happening inside the body more clearly, safely, and in greater detail. While MRI is a powerful tool, it's expensive, time-consuming, and doesn't always give us information at the molecular level. That's where nanoparticles like quantum dots come in. These are tiny semiconductor particles, thousands of times smaller than the width of a human hair, that can be designed to light up specific cells, proteins, or even tumors inside the body. What makes quantum dots so special is something called the quantum confinement effect. When materials are shrunk down to the nanoscale, electrons inside them are squeezed into a very small space. Because of this confinement, the particles interact with light in unique ways. Their color actually depends on their size. Simply by changing how big or small the particle is, we can tune the color of light it emits with incredible precision. For imaging inside the body, near-infrared or near light is especially valuable. Unlike visible light, which is strongly scattered and absorbed by tissues, near-infrared light can travel deeper through skin and organs. That means we can see farther into the body with less interference and less damage to surrounding tissues. By designing quantum dots that absorb and emit near-infrared light, we create bright, highly sensitive probes that allow us to detect disease earlier and track biological processes in real time. So, of course, all of this sounds promising. So what's the holdup? Even the best near-infrared quantum dots are extremely expensive to produce, are extremely dangerous to produce, and are simply underperforming in the status quo, not having enough brightness to take high-quality images. So the goal of this project is to develop easily replicable, highly luminescent near-infrared heterostructures without the use of toxic chemicals. And what we aim to do specifically is identify a key literature gap. Where there's a lot of literature already present on each of these elements of the heterostructure independently, we identified that the indium arsenide to indium phosphide transition, key to developing this highly luminescent structure, remains a literature gap in which we don't understand the science behind it effectively and are therefore not able to make these highly luminescent structures. And by tackling this issue, we can get back to the main goal of being able to address these problems in the medical field. And with all of that, thank you to our collaborators. And of course, thank you to the ARCS Foundation for sponsoring me as a scientist. And thank you all for your time.